Lunch, so we'll dim the lights and I'll speak in a nice soft voice so you can get a nice nap after lunch. I'm going to talk about continuous delivery for architects and 6 ways continuous delivery has an impact on architecture. And I'm going to talk about this in 4 different categories: deployment pipelines, tests, data infrastructure, and some architectural considerations. So let's first talk about some perspective shifts and some architectural considerations for continuous delivery. Some new perspectives that we've picked up in architecture because of continuous delivery. Now, some of you may have noticed that one of my titles with ThoughtWorks is Meme Wrangler. And a meme, as you know about internet memes, is a self-contained viral unit of thought, and wrangle, of course, means to wrangle or herd. And so that's part of my job at ThoughtWorks, is to figure things out and then talk about them. And one of the memes that I wrangled was this observation that very often yesterday's best practice becomes tomorrow's antipattern. And it's an interesting thing to observe, but it keeps happening over and over again. Maybe the most classic example of this is this super famous, went too far there, talk by Edgar Dijkstra about use of goto considered harmful. Because at the time, everybody wrote code in goto, and he suggested that maybe that wasn't the best way to write code, and people thought he was crazy. But then, of course, we created modular and structured programming and figured out that he was right. If you look at something like the technology stack for database stuff in Microsoft.net, about every 2 to 4 years, they completely change it and tell you, forget about that old stuff, that's terrible. The new stuff is the really good stuff. You should, forget about that old stuff, that's terrible. And they keep doing this over and over again. So 2002, and then 2007, and then 2008, they said, no, forget all this, we got something much better. And now they're talking about something on the cloud, and so they keep doing this, and they're doing this to themselves because they keep saying, our next thing is the best thing, and you should forget about the old thing. This may be the best exemplar ever of best practices turning into anti-patterns, because people with a serious face built EJB applications back in the late 90s and then realized what a terrible idea that was. And this is a good example of a place to talk about the definition of an anti-pattern, because an anti-pattern doesn't just mean something bad. We don't need another word for bad because we already have the word bad. So anti-pattern is not just another word for bad. It's something that initially looks like a good idea, but then turns into something that's bad. And of course, that's basically the idea behind yesterday's best practice turning into tomorrow's anti-pattern. But another one of those things that we've realized because of continuous delivery that I mentioned in my earlier talk today, that architecture is abstract until it's operationalized. So architects are really good at doing these lines and boxes view of architecture, but that's really just a flat 2-dimensional view. What continuous delivery taught us is you have to make it run in an operations center with real software and real version numbers, which creates a 3D version of software, but you also have to pay attention to time, because nothing is ever static or stable in software. It's always shifting and changing, and so you have to think about, how am I going to evolve this as well? That's more of a 4-dimensional view of architecture, and this is one of those things that continuous delivery has given us. We've realized that as architects, you can't ignore data and operations and security, because all those things are tightly coupled with a software solution, and you have to pay attention to all of those things. And that is, in fact, the first lesson that continuous delivery teaches us, is that architecture is really about more than just lines and boxes and technical architecture. And in fact, another implication of this, as I alluded to, is the expanding role of architects on projects. Because before continuous delivery, it was quite often that you'd have an engineering silo that had an architect in charge of things, and then DBAs were in a completely different silo, and then operations in a different silo. But as we start thinking about continuous delivery, architects have to become a lot more influential here because things like DevOps have an impact on architecture. Things like data schema design have an impact on architecture. And so unfortunately what this doesn't mean is that the architect has become the boss of all those people, which would be really convenient if that were true, but instead that this has become a much more coordination role than it used to be because you need to coordinate between the DBAs and operations and developers because again, software is one big thing that's hard to separate. And this is the second lesson that it teaches us is that the role of architect has expanded and become much more influential. Whether you have the actual political clout to do that or not, technically that has become true. So let's talk next about a purely architectural subject, which is coupling and cohesion. And some metrics and visualizations that help you as an architect understand how your code base goes together. So there are a couple of metrics here that I'm interested in. The structural coupling metrics, afferent and efferent coupling. Afferent coupling are the incoming connections to some code artifact, and this may be a class or a package or namespace or some other code artifact. And efferent connections are the outgoing connections, the other things that it references. Unfortunately, these two terms are very similar to one another, so there's a great little English mnemonic to keep them straight. Efferent starts with an E, which is also the first letter of the English word exit, and those are the outgoing connections, so that's the easy way to remember afferent versus efferent. And this is really important to architects because you can use visualization tools to see how classes are joined together using these two metrics. And here's one of those tools. This is an open source tool called xray. It's inspired by an old school Smalltalk tool called Code Crawler. And what this does is show you your code base in a slightly different view than you've seen it before, where these is an inheritance hierarchy. The bars are actual classes or interfaces. So, and the way that you read this is that when you look at the bars, the number of lines of code is the length of the bar, and the width of the bar is the number of methods in that class. So let me zoom in on part of this. Knowing what you now know about the way xray draws things, what does that tell you about this guy? Very long and skinny, lots of code, not many methods, kind of smelly. I want to look at that to see why there's so much code there and so few methods. So you want squarer things here, not longer things. And so that's really just about the structure of your code itself. But the other cool thing you can get in xray is how things are connected to one another. So when you click on one of these classes, you can see the dependencies for that class. So you can do this in this bar chart view. When you click on a particular class, you see the other class it's connected to, and the stronger the line, the more connections there are between those two things. And realize this is an Eclipse plugin, so if you double click on one of these, it opens up the class in the IDE, so you can investigate it very easily. But the really useful view in xray is this pie chart view of class. This is package dependencies for a project. And here are the class dependencies. And now you can start seeing where this comes in handy for an architect. Because what if my job were to take this monolithic application and break it into smaller services? Here's the question for you. Should I slice it along here, or should I slice it along here? The first one or the second one? Obviously the first one, because every one of these lines I break, I've got to reestablish over integration architecture if I'm building these as services, and so I want to break as few connections as possible. So this shows you how things are clustered together. Many of you are into this process right now of refactoring a monolithic architecture into some sort of services-based architecture. The first step in that process is improve the modularity of your monolith, because that'll show you where the seams are, and that'll show you where to cut your services out of the monolith. And a tool like this can help you visualize exactly where those clusters and relationships are. As I mentioned, this is a an IDE plugin. Here's a real code base run through xray in this pie chart view. This one's kind of a train wreck. So that's the classes view. Here's the package view. This is what a really terrible code base looks like in xray. This is Argo, but you can click on these guys. So this package shows you all the classes in this package, but this one's going to be a lot harder to untangle than the one I showed you before. So that's one form of coupling that we have to pay attention to as architects, the structural coupling with afferent and efferent coupling, but we also have to worry about temporal coupling, which are things that are bound together in time. And the common thing that we find bound together in time are transactions in a database. You may have some business process that touches several different classes, but they're all coordinated together within a transaction. That is a form of coupling, just like afferent and efferent coupling is a form of coupling. And if you're doing some sort of restructure of your architecture, you have to pay attention to this coupling, just like you have to pay attention to structural coupling. And so the point of this is that you need to understand the structure of your code as it evolves. You need to be able to get visualization tools and understand how the pieces fit together, particularly if you're trying to do some sort of migration or some operation like that. It's really important to be able to understand what you actually have before you start trying to make a bunch of changes to it. So that's a bunch of stuff about coupling and cohesion. Let's talk about components and services. And in fact, the continuous delivery book says very little about architecture. In fact, the main piece of advice the continuous delivery book gives you about architecture is to use components to decouple parts of your application that change at different rates. It turns out that's one criteria you can use to componentize things, but there are other criteria as well. And in fact, component is too broad a term here, because we have two kinds of things that we deal with typically as architects that are both components. We have libraries and we have services. Libraries are compile time dependencies. So these typically are represented as jars or .NET assemblies or Ruby assemblies or some other packaging mechanism like that, and typically managed through compile time dependencies, versus services, which tend to run in a separate process and communicate over networking mechanisms like HTTP or TCP/IP. And it turns out the engineering practices for these two kinds of things are different. So let's talk about each one in turn, and we'll talk about components first. And libraries. So let's talk about building applications that consist of a bunch of dependent libraries. So let's say this is what my application looks like. I'm building this portfolio management application. I have a framework that everything is based on, and then reports, settlement, and pricing engine extend from framework. So does portfolio management application, and then I have this pricing library thing that's a third party from the internet, from some Maven repository or something like that. So when you start constructing applications that look like this, one of the things you have to do is figure out how to manage the dependencies between these pieces of your application. And most people's, in fact, this crowd may actually be too young for this, which is depressing to me, but most people's first real experience with managing dependencies and transitive dependency management was this thing we used to call DLL hell in Windows. Because when they created Windows originally, hard drives were precious things, and they were very small, and they didn't have enough room to build all these things as statically linked libraries, and so they built the core as this dynamically linked library and then wrote all these applications. Of course, the problem was people would update one of those core DLLs and break a bunch of other stuff, and that was transitive dependency management. This is actually a great example of yesterday's best practice becoming tomorrow's antipattern, because hard drives got bigger almost instantly, and it took a decade and a half to untangle the DLL hell that we created because of that architectural choice. But from a practical standpoint on projects, we have two approaches for managing dependencies. The ubiquitous live directory that you have in your project, where everybody feels free to add stuff as much as they want, but nobody ever removes anything. because you're terrified. If you remove something from the live directory, you may accidentally wreck the entire earth. So nobody ever touches anything in that magical live directory. I'll show you a tool in a second where you can actually remove some stuff from the live directory that you're not using anymore if you want to. Or a transitive dependency management tool, and all platforms eventually end up with a transitive dependency management tool because it's just too hard to deal with otherwise. The Ruby on Rails world, this really hit them between the eyes about 2 years ago, and they were not happy of having to start dealing with transitive dependency management, but every platform eventually reaches this spot. So let's talk about some anti-patterns that show up in components. And one of those is cycles. I mentioned this earlier today as well, circular dependencies that show up when you have something that references something else that eventually references the original thing again. This is particularly egregious in languages that have super powerful IDEs. Because let's say you're a Java developer and you're coding along in Eclipse and you reference some class that you haven't referenced before. What does the IDE do for you? It pops up a dialog that says, you want me to auto-import that for you? And you swat that dialog away so fast you don't even see it anymore. If I came to you 5 minutes later and said, did you just import some dependencies? You're like, no, I swear I haven't imported anything in like a half an hour or so. So you don't even see that dialog anymore because it's just so automatic. Just bam, and you're on with your work. But what you're doing is creating cycles in your code base. Really powerful IDEs aggravate this because what you really need is some sort of obnoxious little clippy thing that as soon as you do that auto import pops up and says, should you be importing this library or should you be doing something else with it? But we don't have that. But we do have something that's just as good. The problem, of course, is that cycles make the system hard to componentize and it makes the life cycle more complicated because I can't just reuse this class now. I have to bring the whole bundle of them together, which of course hurts reusability. So let's talk about how to fix this problem. This is an open source tool by Kirk Kernerschild, and I talked to him recently. He actually wrote this tool a long time ago, but it's still the most downloaded tool on his website. This is a tool called Jar Analyzer for the Java space. You can take that live directory and run Jar Analyzer on it, and it will show you how things are connected to one another. And so if you run this on your live directory and you come up with some orphans that nobody's connected to, you can safely get rid of those guys finally and not worry about breaking the earth unless you're doing something crazy with reflection or something like that. But the other really cool thing about Jar Analyzer is it also graphs these dependencies for you. And this is what happens if you don't pay attention to dependencies in a Java ecosystem, because here is the Jar Analyzer picture for Struts 1.0. And here's the exact same picture for Struts 2. Yikes, that's terrifying. This is what happens when you let your dependencies just run rampant and run out of control, because how are we going to reuse any of this now? This has now created a spider web of awful tangles. This is the only commercial tool that I talk about here because it's the only tool that does what it does that I know of. This is for the Java ecosystem, Structure 101. There's a similar tool for the .NET ecosystem called ndepend. What Structure 101 does is analyze your code base and find cycles for you, and it gives you a to-do list of refactorings. If you'll do these refactorings, then you will have eliminated that cycle. So Structure 101 is a tool that lets you clean up all the cycles that exist in your code base. And in fact, these guys just announced a really slick new tool that is based on Structure 101 that gives you a live view of the dependencies for every single thing in your Java project. It pops up a window and you can point to a single field in a class and it will show you all the places where that's used. It shows you graphically how things are connected to one another in real time. Really slick, really nice piece of work, and that's just about to come out from the Structure 101 guys. So let's say that as an architect, you went and used Structure 101, or you used Independ, and you went into your code base and untangled all the cycles. How are you going to keep them from coming back? Well, you could institute a policy that says any developer who institutes a cycle, there will be beatings at lunch on Friday, which is not a good policy because it's just too hard to remember all these details all the time. What you want is an automatic mechanism that can catch this problem when it happens, which of course is a place for a unit test. Now this is what I call the fitness function in my evolutionary architecture talk, but it's really that, but it's just a unit test. And this is using JDepend, an open source tool in the Java world, which because it's written in Java has a Java API, and you can use it to test a single package to see if it has cycles, or you can test all packages to see if any cycles exist in your code base. So as the architect, when you've gone through and chased all the cycles out of your code base, put this unit test in place. And now, as soon as a developer uses a too-friendly IDE and accidentally introduces a cycle, you get a failed unit test before they check code in, and they realize, oh, I've introduced a cycle, I should not do that, because that's a bad thing. This is what we're calling an architectural fitness function, atomic batch fitness function from an evolutionary architecture standpoint. The other slick thing about JDepend, as I mentioned this morning as well, is you can define dependency directional rules if you want. So if I have three packages here, EJB, web, and util, I can define how these things should be related to one another. So it's okay for EJB to depend upon util, and it's okay for web to depend upon util. But if some developer comes along and imports web into util, it's going to fail this unit test. So this, again, as the architect, allows you to control the structural integrity of your code base by using tests that are designed to catch common kinds of bad things that developers accidentally do to code. This is what we refer to as an engineering safety net. Rather than build a lot of really elaborate draconian policies that nobody can ever remember, instead just automate the verification of those things, and now they don't have to keep this in their mind all the time, they just have to react to it, developers react to it as something like a test fails. Here's the other thing we want to be able to do, and this is one of the reasons you'd like to untangle some of these dependencies, is we really want to be able to build pipelines to build applications. So when I make a change to a component, I want that component to rebuild and then automatically kick off rebuilding the application itself, so that now what I've done is move the unit of change even smaller. So the smaller unit of change means it's easier to incorporate that change and then incorporate that into a deployment pipeline to vet the correctness of the entire application. Here's another component-based anti-pattern, diamond dependencies. Here's the scenario. Let's say that you've updated framework and made a change to it. As soon as you update framework, all the downstream dependencies are going to want to update themselves, and reports engine incorporates the change to framework, and everything's cool. All of these tests are green. But when the pricing engine tries to incorporate that change to framework, something goes wrong. We got some test failures, something is just not right in the world. Now the $64,000 question is, which version of framework should portfolio management application depend on? And the answer, of course, is none of the above. There is no legal descendant or progenitor for the application itself because two of its dependencies have different versions of the same framework. This is an annoying problem on the internet at large, and we have a bunch of tooling to help solve this problem. For your applications, though, this is actually quite easy to fix. Because what you need to do is make sure that you build each level of dependency before moving on to the next level. So in the scenario I have laid out here, we're going to set up our deployment pipeline to compile framework upon change. Any change that happens to framework would have built all three of these guys, pricing, settlement, and reports. And if any one of those fails, We don't try to rebuild the portfolio management application. Only if all three of these are successful do I try to then promote and build the application itself. So always resolve a level of dependencies before you move to the next level of dependencies, and you can fix this diamond dependency problem. So that's a bunch of stuff about components. Let's talk about services. One of the things you'll realize, as I mentioned, many of you, I suspect, are probably decomposing some sort of monolith into some sort of service-based architecture. And one of the things that you realize pretty quickly as you walk down that path is that service-based architectures promote coupling from internal application coupling to external integration coupling. Here's what I mean by this. When you have a monolithic application, you have a whole bunch of classes inside that are collaborating and doing stuff. They're calling methods on each other. You're not that concerned about latency because if one of these guys calls a method 1,000 times, it's all in process, so it's all going to happen pretty fast, so you're not that concerned about it. But when you start breaking these things into services and finer grained than the monolith, now, each of these services still have classes inside them, but now we're having to make calls over the network to make things happen. And now, all of a sudden, all these network concerns are up in your face where they never were before when you were dealing with internal application coupling. In fact, there's a famous list of things that typically nab people when they move from application architecture to integration architecture. And this is a list that Peter Deutsch came up with at Sun Microsystems back in the late 1980s. And it now has its own Wikipedia page called The Fallacies of Distributed Computing. These are all the stupid assumptions you make as you move from internal application architecture to some sort of integration architecture. Stupid assumptions like the network is actually reliable and it works when it's supposed to. That latency is 0 and that everything happens instantaneously, because it kind of does in your application, but definitely not on the network. That bandwidth is infinite and you don't have to worry about problems with capacity. That the network is secure. That the topology doesn't change without telling you, and when it does change without telling you, that there's one administrator you can go talk to and complain about the topology changing without telling you. None of these things exist. Transport cost is 0, that's another one of these fallacies. And that the network is homogeneous, it's all the same thing. In a lot of cases, it's a lot of different things. And so these are all things that nab you as you move from application to integration architecture, and you have to pay attention to those things because it will make a big difference. And so what that means is, when you move from a monolith to a service-based architecture, you have to be a lot more explicit about coupling points. Think about how things are connected to one another. Think about what kind of information needs to pass from one thing to another. Because the last thing you want to do is do a query in a database and gather up 100,000 customer records and then shoot them over your network through SOAP or REST or something like that, unless your goal is to create the slowest architecture on earth, which you will have achieved. We also use a lot of engineering safety nets in this world, things like consumer-driven contracts and other sorts of testing to make sure that the things that we've established stay established and don't break over time. This forces a coarser-grained coupling of your services. You tend to think in a monolith of all these things as being tiny little behaviors, but here you're really trying to capture coarser-grained things that are related to one another. So if this is the microservices world, for example, this would be all the things within a bounded context. But it doesn't have to be as elaborate as that. It's all things that are related to one another in some significant way. You have to be careful because undisciplined coupling here can become a real mess. I refer to this as the Visual Studio problem, because in Visual Studio, you could take your monolithic application and spend an afternoon just right-clicking on every method and making it a remote endpoint. And by the end of the day, you will have the slowest distributed application on Earth. Congratulations. So if you're really undisciplined about this, you can create a real mess without thinking about granularity and just exposing methods as endpoints and not worrying about what information goes into them. And now coupling dynamics become integration issues. One of the things that's really convenient in this world is transactional behavior in databases because you have a monolithic application, monolithic database. That's super easy. But now temporal coupling is going to nail you when you move to service-based architecture. You have to start thinking a lot more carefully about how things are related to one another. So let's talk about different kinds of service-based architectures. And I'll do this relatively quickly, but there are three main flavors out in the world: microservices, service-oriented architecture, and a service-based architecture. Let me talk about the distinction between these guys. And I'll talk about service-oriented architecture first, which we don't build a lot of anymore, but has some really interesting lessons for us. Because one of the goals in service-oriented architecture was a really strict taxonomy of services. Every service had a very particular kind of place that it lived in this architecture, and very specific kinds of things, responsibilities that it had in this architecture. For example, the business services at the top here, these are the top level things that we're in the business of. So these are designed to be extremely abstract and probably created by business people. The implementation details for those business services are here in enterprise services. You have one-off application services, you have infrastructure stuff, but all these things exist in really strict categories. And of course, the message bus thing in the middle, which is the defining characteristic of this architecture. This architecture is all about abstraction. It's about creating a service taxonomy. It's about trying to create a really intense shared resources kind of architecture. It's worth probably mentioning here, parenthetically, that architecture is a little like modern art. You can't look at it outside of its context and make any sense of it. So when you look at service-oriented architecture now, it's like, wow, there was a lot of effort here into things like shared resources and building these big application servers and clustering and all that sort of stuff. But you have to think about the ecosystem that existed when SOA was popular. Because at that time, operating systems were expensive commercial things. Application servers were expensive commercial things. Everything in software cost a lot of money. And so there was a strong external impetus to keep things as cheap as possible by getting as much stuff to run together as possible. So it is a very shared resource kind of architecture. If 10 years ago, as an architect, you'd gone to the head of operations and said, hey, I've got a great idea for this new architecture. We're going to take every single business process and run it in its own service, on its own computer, and its own operating system. And we're going to have like 60 of them. And the head of operations say, get this lunatic out of here as fast as you can, because there's no way I'm buying 60 operating system licenses just so you can have one operating system per service. That's the stupidest thing I've ever heard. But now, of course, we can do that because all that stuff's free. But you have to think about what ecosystem it grew up in. We could not have done microservices now because it was not financially feasible to do microservices. So this is a very intense middleware kind of architecture and a real focus on heavy interoperability. Which brings us to the polar opposite, the most popular kid in town right now, which is the microservice style of architecture. And of course, the defining characteristic of this architecture is this idea of a bounded context, where each one of these services is completely isolated from the others. I did that too fast, let me go back for a second. The real goal of this architecture is to maximize easy evolutionary change. And so the idea is that I can take one of these services and pop it out and stick another one in its place and not break anything. So this is much more of a Lego kind of a way of doing services than something that's extremely coupled together. And there's a great quote by David Wheeler that says, we've been sold this idea that software reuse is like Lego blocks, but it's a lot more like organ transplants than it is Lego blocks. And I think that's probably true. But one of the tricky things about the microservice style of architecture are things like the insistence on the bounded context all the way to the database level. So let's say that you're migrating some monolith into microservices. And architecturally, everything's cool. But then you go to your DBAs and you tell them, hey, you know the schema that you've been carefully stitching together for the last decade? Now we want you to take that and explode it into all these little tiny atomic things and to manage all the integration points between that. They're going to love you for that. Because this is not part of their job. They're not interested in doing that. And in fact, it may not be feasible or even desirable to undertake that massive kind of database refactoring, which brings us to this idea of a service-based architecture. It's still domain-centric like microservices, but it does not have quite the strict kind of partitioning rules that microservices have around things like data, around things like service size, and the use of things like an integration hub, which you may use a little bit to help you with integration points, which is generally verboten in the microservices world, but much more common in service-based. This is basically a compromise architecture between a monolith and microservices that tries to attack the main pain points like data, service granularity size, and integration. And there are a bunch of variants of this that may start introducing a lightweight message broker. This is particularly good if you're in a super integration heavy kind of environment, because message buses are great for paving over integration point headaches. And so as long as you don't put a lot of business logic in it, it's a great way to manage a lot of legacy connections and other sorts of things that you'd rather not have to make major changes to, but rather just kind of integrate to. So let's talk about some distributed architecture challenges when you're building things with services. One of these has to do with contract creation, maintenance, versioning, and coordination. Because if you have client applications using something like an event queue to call some sort of service component, there is a contract that exists for these guys, and they all have to agree on what that contract is. How do you manage things like contract changes without breaking stuff? This is a challenge within distributed architectures, and there are a variety of different ways to solve this. One of the ways to do this, and in fact the typical way that we try to do this, is not expose the versioning information out into the architecture itself, but rather hide it underneath the service component. So in other words, the service component, when it gets a request, says, which version of this did you want? And now I'll give you the versions you wanted back, versus spilling version numbers out into your architecture, which just leads to a bunch of headaches. You can also use mechanisms like consumer-driven contracts to protect these integration points and make sure that they still adhere to the right contracts as things change over time, particularly if different teams own these client applications. You want to make sure that you agree, and consumer-driven contracts is a great way to do that. You also have to worry about, this is from the distributed computing, fallacies of distributed computing, things like latency. So remote process responsiveness and server availability. What happens if you can't get to the event channel? What happens if the service component is not available? What happens if the latency is too high? So all these things you have to think about if you're building some sort of integration architecture with services, including the fact that what about timeouts? Should we set a timeout? Should we set a circuit breaker? There are a bunch of practices in the DevOps space to manage that. You also have to worry about timing and latency. So when you're making a direct call from a client to a service component, it's going to be as fast as it can be. But now when you start adding the levels of indirection through things like message queues, each one of those adds a time component to that invocation. And so you may find yourself in a situation where it's taking way too long to actually get through all the levels of indirection you set up for perfectly legitimate architectural reasons. But then when you see the final performance, you've got to make some changes to it. And you also have to worry about things like authentication and authorization for remote connections and service invocations. So we have a good client and a bad client. My service component needs to be able to take requests from the good client and block ones from the bad client. And so there are various mechanisms you can use to solve that problem. Also a common problem, distributed architectures. It's also really common to do logging in distributed architectures to give you a holistic view of things like transactions. And so using log aggregators is a really common practice here because particularly if you have a really highly distributed service-based architecture, getting things like business transactions and making sure they resolved and the timing of how long it took to resolve those things can become interesting. And so using logging facilities and monitoring helps you out a lot with that. We refer to these as continuous atomic fitness functions in evolutionary architecture. And then transactions, which I mentioned before. Transactions typically help you define what your business processes are. And in general, you do not want to go to distributed transactions unless you just absolutely have to, because distributed transactions are really, really hard to get right. And distributed rollbacks are even harder to get right. Almost always, when you get to the point where you're doing distributed transactions, you have made a granularity error in your architecture. You've tried to go too granular, and now you're having to wire things back together with distributed transactions, which is not a good look. And so business processes have natural seams in them, and transactional boundaries are one of those seams that live in systems. So as the architect, you need to be able to identify those things, and that helps you find the right granularity for services. One of the common misnomers of microservice is that people mistake it because microservice is a label, not a description. And that's a really important distinction. Martin Fowler, who popularized this term, makes this distinction because when Martin and Fowler and James Lewis wrote the first article about microservices that really named this architectural style, they had to come up with some name for it. And they named it microservices in contrast to service-oriented architecture, which could be called gargantuan services. And so these are definitely smaller than that, but that doesn't mean that every one of your microservices has to be this teeny tiny little thing. It should be the right size for the bounded context you're modeling. And some of those may be quite large. In fact, if you look at the original article that introduced microservices, they talk about several services in that article that are actually quite large because they encapsulate a business context. So don't try to pick a shiny architecture and then make your business process fit that architecture. Sometimes that doesn't work, and there are natural kinds of architectural fits for some kinds of problems. This bounded context idea from domain-driven design has become very, very popular. In fact, you could say that it is basically the bounded context idea from domain-driven design married with all these engineering practices from continuous delivery that gave us the microservice architectural style, because the assumption within that architecture is these kind of advanced engineering practices. And in general, what we've seen is a move to more domain-specific architectures, moving to more of a bounded context kind of world in microservices and service-based architectures. Even if people are not going all the way to microservices, they're tending to build more domain-centric stuff than purely technically architecture-centric stuff, just because of the way team impacts work and the kinds of common things you work on a daily basis. It turns out that domain-based partitioning tends to allocate workforce better than having a technical architecture partitioning. Another common refrain in this world is to prefer choreography to orchestration when you're sending messages between services. And here's what I mean by that. If you look at the traditional service-oriented architecture enterprise service bus pattern, a lot of the really important business processes were defined in that enterprise service bus. From an architectural standpoint, that's a coupling point, but it also acts as an orchestrator. So it's called an orchestrator because it's like the conductor of an orchestra. The message bus tells people what to do and what order to do them in, etc. That's orchestration. A more popular style in microservices is choreography. In this world, we don't have a central repository managing all this stuff. Instead, if two services need to send stuff back and forth between each other, they just send messages back and forth to one another and resolve whatever differences in message formats they have on a case-by-case basis. One of the interesting side effects of having something like an enterprise service bus is that as soon as you introduce an enterprise service bus, a pack of enterprise architects will accrue to that like barnacles in the bottom of a ship in the ocean. And before long, they will become a political force in your organization, and it's only a matter of time before they tell one of the service teams, no, you can't put that service on our precious message bus. And now they're more political than they are technical, and that happens a lot within companies. And part of this is because of Conway's Law. When you build that communication structure, people will form around it because of Conway's Law. But this sounds kind of frightening, because if we don't have central coordination for things like communication between services, and we're allowing these services to modify themselves in any way that makes sense for that team, how can I make sure that these integration points just don't break all the time? For anything in microservices that sounds wildly impractical or impossible, there are good engineering practices to solve that. And there's a great example here, this idea of consumer-driven contracts. I talked about this as a holistic fitness function in evolutionary architecture, but it's heavily used in microservice kind of environments where you have the service provider on the left and they're providing some information, maybe overlapping bits of information to the three teams on the right. The idea of consumer-driven contracts is the consumers will put together a set of tests and hand it to the provider. And the provider now promises, I will keep these tests green always. Because those tests encapsulate what we need from an integration standpoint from the consumer to the provider. As long as the provider keeps those green, then everything is cool. So if this guy makes a change and doesn't break anything, then he evolved in a way that nobody else cares about. If he did, in fact, make a change that breaks something, that becomes a placeholder for conversation to get together with those two teams and reestablish a new set of contracts. Now, there's something important implicit here in this discussion, and that's a certain level of engineering maturity in terms of continuous delivery. Because if you're a company that routinely runs around for 2 or 3 days at a time with a broken build, this is not going to be a happy place for you. Because in this world, broken builds may mean that integration doesn't work anymore, nothing works anymore. And so there's an assumption here, a certain level of maturity that we can keep all of our builds green all the time, and we're running our tests every time we make a change, and we're being responsible professional engineers about this. And this is, in fact, the long number 4, which is manage coupling intelligently. Whether that's structural coupling, where you're building monoliths or building services and trying to analyze them, whether you're building things like domain-centric architectures inspired by Eric Evans' book, looking at semantic coupling between the pieces of your ecosystem, and transactional impacts, and also organizational impacts. All these things are a form of coupling. And one of the things you have to manage as an architect in this kind of world is to manage all these different coupling points intelligently and make sure they don't start fighting with one another. So let's talk about some engineering practices. And a really common thing that came as hitched a ride along with continuous delivery is all the DevOps machine provisioning stuff. Where you can manage lots of systems, manage configurations programmatically, enforce consistency, and treat infrastructure as code. In fact, one of my colleagues, Keith Morris, just wrote an O'Reilly book about infrastructure as code as a way of managing this as an engineering practice within your projects. This is actually one of those things that for a long time people thought was impossible. Now, there's just no way you could write the source code for a computer, but this is a great example of innovation and pressure in the agile world. because we really wanted this in the Agile world, so we were applying pressure. We need to solve this problem, and eventually people solved this problem. And now we have lots of solutions to this problem, even the next generation stuff like, for example, Docker sits on top of all this. So let's talk for a bit about deployment pipelines. Because typically on a continuous delivery kind of project, the architect is going to be the one responsible for putting the deployment pipeline together. And this is sort of like continuous integration on steroids, in that it triggers every time you make a change to your code. And when it does, it mimics the first stage, mimics continuous integration, where you pick up source code and commit tests and build scripts. You compile, you run unit tests. This assemble stage, because this is just the first stage in a pipeline. And I'm going to compile a bunch of stuff here. There's no reason for me to compile this again at every stage. In fact, it's a big waste of time, and it introduces the possibility of getting differences creeping into something that should be deterministic. And so what that assemble stage says is whatever artifacts we created here that will be needed in the next stage of the pipeline, push those over to the file system. So this artifact repository, that's the common name for it in continuous delivery, but that's not like Artifactory or an actual repository. That's just file system, but it needs working space in the file system. So all these compile classes and jar files get copied over there so the next stage can pick those up without having to redo all that work. And this is typically where you do things like code analysis. So just like CI, this is run against every check-in, starts building a release candidate, and if this fails, you fix it right away. Unlike CI though, this is only one of a stage. And it's up to you to figure out what stages you need in your deployment pipeline. So the first one will probably be commit unit tests, maybe you run some functional tests, maybe user acceptance testing, maybe staging, maybe there's a QA, automated QA that you run. This is going to be part of the job of the architect, is figure out what stages do I create in my deployment pipeline to be able to verify the correctness of my code. These are, of course, all joined together by that artifact repository. The real overarching goal here is increased confidence in production readiness. And so really what pipeline stages are feedback opportunities about, have I made it this far in my engineering for the solution, and this far, and this far. As you move down those stages, each one of those stages should be more and more sophisticated and put it through more and more rigorous kinds of testing and verification. There is one stage, though, that's considered special. And it doesn't have to be the user acceptance testing stage, although that's the one I've highlighted here, but that's the one where you start doing machine provisioning as part of the deployment pipeline. And so it is expected at some point in your deployment pipeline that one of your stages is going to start configuring environment, which means I'm going to programmatically build up the deployment target for this code and then deploy code onto it and then run a bunch of tests on it. This is end-to-end test in a production-like environment, as close as you can get to something that looks like production, triggered whenever the upstream stage passes. And this is the first DevOps-centric build. But remember earlier today when I was talking about the role of architects expanding? Back in the day, as the architect, you didn't really have to worry about the operational aspects of the code until the very end of the project. And that's when you'd start scheduling meetings with operations and those guys, start talking about what kind of resources we need and allocation and all that sort of stuff. You do not have the luxury of doing that in a continuous delivery project because you're expected to start building out the target machinery from day one as part of your deployment pipeline, which means the architect is going to have a much closer relationship with operations because now we're doing part of operations job as part of our regular build process, as part of our deployment pipeline. So this is part of that expanding role of architect that needs to be able to liaison and work with operations from day one, not at the very end of the project. Now, clearly we love automated things in the continuous delivery world. because that's the real key to getting things really fast and getting a lot of stages done in a short amount of time. But we also realize, we're pragmatists, that you can't automate everything. As much as we would like to, legal verification of your code. You may have auditing requirements of your code where an auditor has to look at your source code every time you make changes. And so deployment pipelines can accommodate manual stages. And it works the same way. So let's say you're doing an exploratory QA as a manual stage. So now someone from QA is going to go to the deployment pipeline and say, I'm ready to work on this. That will be a pull instead of a push. So it'll do the same configure environment, build out the environment, but now along this red line, you're going to do whatever manual process is required, which may take hours or days or weeks. When you're done, you tell the deployment pipeline tool either pass or fail, and then it will do the next thing it's supposed to do, which may be an automated stage or another manual stage. This is common in UAT or staging or integration or production. If you're not doing continuous deployment, then you probably have a manual stage to push code into production. That's continuous delivery, not continuous deployment. That's the distinction between those two guys. I talked about this push versus pull model. The push model says, if I'm successful in this stage, automatically try to make the next stage successful. But if there's a manual stage and QA is halfway through doing their QA and a new build comes out and clobbers what they've done, that's rude. So this is a pull model where a manual process, a person says, I want the latest copy of the code, and they work on it and then pass or fail. And in any case, all of these things are as automated as possible in terms of machine provisioning and building up machinery. So this is the whole deployment pipeline on one page, and you'll notice that once we pick up configuring environment, we don't give that up. Every stage in the deployment pipeline should be more sophisticated than the one that came before it and build on the assets from the one that came before it. There are a variety of tools that allow you to do this. Jenkins has several plugins that let you wire together pipelines on top of Jenkins. It's a little bit of a hack though, because one of the things you want to check in your pipeline is the cycle time, which is how long does it take to run through the pipeline. The problem in Jenkins is there are no properties that span projects, and so there's no way to calculate the time of a whole bunch of projects to trigger other projects. There is a phenomenally good tool designed, purpose-built for this, open sourced and created by ThoughtWorks called GoCD, which does all this stuff. And then some, built to be industrial strength. Here's an example, for example, of 3 different repos that have catalog, orders, and web app, and I've built an integration point here in my deployment pipeline. And so now, anytime one of these guys changes, it automatically triggers the downstream stages and tries to build those guys. So this is it building those. You get the VCR controls for these guys. So now it's successful, and it successfully built that. And you can also see dependencies as you mouse over things here. You can see which things relate to other things, which is really nice in very complex environments. You can also build good integration pipelines in GoCD. So for example, here I have catalog orders in a web app. I have an integration point here, and once I've run some tests in integration, then it's going to go to UAT performance and production, so you can do all these things in parallel if you want to. You can unify and test one thing and then do a bunch of things in parallel. So it gives you a lot of flexibility over how you control your deployment and deployment pipelines. And in fact, one of the really useful things that deployment pipelines allow you to do is this idea of a fan out, which lets you build 2 things in parallel and test them against one another, which is really common in continuous deployment kind of scenarios. And here's an example in GoCD of a fan out where I have my web application, I hit my integration point, and then it fans out to a bunch of different environments that I want to run in parallel to speed them up. So there's my agenda again. One of the other things that's worth talking about here that I talked a lot about in my last session is feature branching versus trunk-based development. We're big fans of trunk-based development, and we do not like feature branching because feature branching creates a bunch of engineering headaches for you. You always have a big scary merge when you do feature branching. Opportunistic refactoring is really difficult when you're doing feature branching because if you live on a branch and you discover something that's wrong, if you refactor and change that, it's just going to make your merge conflict worse when it comes time to actually merge that. And it's really hard to get combined features. We're much bigger fans of trunk-based development, using things like feature toggles. And in fact, one of my former colleagues, Paul Hammett, has created a fantastic website called trunkbaseddevelopment.com, where he's collected all of his writings about trunk-based development, including his experience at a mythical company he calls Bookface, about how they do trunk-based development. He has a lot of illustrations of how that works from a practical standpoint. And that is, in fact, number 5, mature engineering practices. You must be this tall to do microservices. And this tall means that you have good engineering practices, you can test, you have good clean builds, and you can build good automation. Last thing I want to talk about are deployments. Rich Hickey, who's a great, the creator of the language Clojure, is also a great word fan, a great fan of older words, and he has resurrected this archaic word for us called complex. To complex something is to intertwine them or braid them together, so I'm complecting this by braiding it together. Lots of problems in software come because we accidentally complex things together that shouldn't be together. One of those common things is for most of you, when you deploy components, you are also releasing features at the same time. You've complected those two things together and driven the risk of both of them up because you're doing them both at the same time. A really common practice in this world is to separate component deployment from feature release. And you can do this with either feature toggles or selective routing. And so this is what I was talking about in incremental change in evolutionary architecture, where components are deployed in this world, and you can vet the operational characteristics of the component without dealing with their features yet. At some point later, you turn on features, either by routing to them or turning on feature toggles. And in this world, applications consist of the routes that you defined between these services. And as I mentioned before, a common trope in this world is being able to introduce a new service, allow people to migrate to that service as they need it, and then eventually get rid of the old one that's not needed anymore due to monitoring and logging and other sorts of modern practices. This is this idea of incremental change in an evolutionary architecture that I talked about before. And that's number 6. These continuous delivery practices lead you toward the things that you need to build an evolutionary architecture. The things you need are things like deployment pipelines, good control over things like coupling and cohesion, the ability to run tests and fitness functions and other things. These are all dependencies on continuous delivery. And in fact, I have a theory that the companies that haven't implemented continuous delivery yet, it's because they view it as a condiment technology. Evolutionary architecture is the thing that's going to drive a lot of people toward continuous delivery because it's required to do a real evolutionary architecture to have all those things in place. And so this may just be a building block for capabilities that you want later. So to summarize all this stuff, yesterday's best practice is tomorrow's antipattern, the expanding role of architect, understanding the shifting structure of your code base, mature engineering practices, manage coupling intelligently, and move toward a more evolutionary architecture. Looks like I have 14 seconds left, so I nailed the time just about exactly right. Thanks very much for coming, and I hope you enjoyed it. Thanks.